Okay, here we go, guys. All right. Here we go. Now, so the first question that we answered was, let's do it, where we have A as Cl and Cl, okay? And it goes to Cl, Cl like that, okay? Where you have the complete, is that on the screen? Okay. Is that, you have that reaction, and then you have this reaction, Na to Na plus 1 plus an electron. Okay? Which reaction is endothermic? And we reasoned, we already did the problem, and we reasoned that, let's look at B first, okay? That in order to remove that electron, even though it wants to get rid of it and it will attain a noble gas configuration, and if you're going to give it to chlorine, chlorine's going to accept it, yes? And then sodium will become positive charged, right? But we're not talking about a situation. You know what? Let's write that down. Let's go like this. Let's do that as well, okay? Now, so what we see here is which one is endothermic, okay? Well, this is not forming a substance. It's just getting rid of that electron. And in order to get rid of that electron, you need to put in ionization energies, yes? So you're not going to, you're going to have to put in energy. It may not be a lot of energy relative to the amount of energy you would need to ionize argon, but it still you have to put in energy. So the total sum of the energies is going to be endothermic, yes? Here, this may be endothermic, but giving it to this will be very exothermic. So the sum is going to be exothermic, the sum of the reaction. Even though that's endothermic, that's exothermic, the sum is going to be very exothermic, correct? Even though you're getting rid of that electron, fair enough, that takes energy, but the sum of the reaction. Okay, here, you're forming argon electron configurations for both chlorines. So that's going to be very stable. So that, you can just reason it through that that's going to be exothermic because you're going to increase stability. The concept in thermodynamics with enthalpy is, if you increase stability, you're going to decrease enthalpy, internal energy. Yes? For instance, when wood burns because the carbon dioxide and the water are very, very stable relative to the wood or the hydrocarbon you began with. Well, how do you know it's stable? Well, this enormous energy was given off in the form of heat. This plasma we call fire was given off. And so you're decreasing the internal energy of the reactants, the wood and the oxygen. You're not just getting it from the wood, you're getting it from the wood and the oxygen. Clear? Don't think that it's all coming from the wood. It's coming from a combination of oxygen and wood. Okay? Get it? That's an important thing that sometimes people forget. You're not just getting it from the wood, you're getting it from a combination of the wood and the oxygen. And that stability of that combination versus the stability of the carbon dioxide and water. You're assuming complete combustion. Okay, so that's that. Okay? Now it says what does it say in the answer? It says only one of the processes involves the separation of particles. In this case, a negatively charged electron is separated from a positive ion. It's an awfully simplistic explanation, but fair enough. Understood? We're off.